Hey, you guys, this is Mr. Sal. Thanks for watching. This is Dilations Part 2, so we're looking at more dilation stuff. So thanks for watching, and please subscribe. Dilations Part 2. We got this quadrilateral named Quad, and then we got Part A. Create a new quadrilateral whose side lengths are 2 times larger than the side lengths of Quad, with the center of dilation at the origin. And label the image Q prime, U prime, A prime, D prime in the space below. Describe the method you use to create your new quadrilateral. So there are several ways to do these. Just if we were to start with D, and we're going to make this 2 times as big, so we do have the origin radical, and D is up to the right 2, which is a scale of 1, so we're going to double that, which is going to make it 2 times as far away from the center of dilation. We're going to go up to another right 2, and that is where D prime will be. Let me clean up that line though. Now we could use the same method for Q, however, we can see that this line radical is 2 units apart, Q and DR. So to double that, we're just going to make Q 4 units apart in the upwards direction from D prime. So another way to do this, I guess it's the same way, but for A, we can see that it went up 4 and then to the right 8 radical. So we're just going to double that. We're going to go up another 4, and we're going to go to the right another 8. So this point radical, let me clean that, is A prime. Next up, we've got U, and we'll transform that into U prime. This time I'll use the slope just from A to U, just kind of like we did with D and Q. So this is 2 to the left and then 2 up. So I'm going to go 4 to the left and then 4 up. And this radical would be U prime. Now it doesn't matter which method you use, it just needs to be right there. Let me clean up the rest of this too. So now that we have those 4 points, we just need to connect them with a line. Bam. And now we have expanded it to make it 2 times as big. Based on what we have learned so far about dilations, what are some ways you can verify that the side lengths of your new quadrilateral are in fact 2 times larger than the side lengths of the original? Well, just about dilations, we use the sloppage, for example, to find the length or the distance between A prime and U prime. We just doubled it from the sloppage of A to U. So we looked at this, 2 to the left, 2 up, so we went 4 to the left and 4 up. That guarantees that the side length will be twice as big. Otherwise, you're using the Pythagorean theorem for these, which is not really what we're looking for radically. Alright, see, this time create a quadrilateral whose side lengths are 1/2 the sides of the side lengths of quad, with the center of the dilation at the origin, and we'll label this one, this image, quad double prime in this case. So let's go ahead and cut this thing in half, starting with D first. So once again, we can look at the sloppage on these, which was up 2 to the right 2. And from the center of dilation, we're just going to cut that in half, both of those lengths. So instead of going up 2, I'm going to go up 1, and then to the right 1, which gives me this point. And that would be D double prime. Alright, same thing with these other points. For example, A is 4 up, and then to the right 8. So A double prime will be up 2, and then to the right 4. Radical. Alright, so there it is. A double prime, let's clean this up. Q as well. This one is up 4 and then to the right 2. So we'll cut those in half, up 2 to the right 1, which gives us this point, Q double prime. Now for U, again, we can compare it to A though. So again, we went to the left 2 and then up 2. So we're going to cut both those in half. We'll go to the left 1 and then up 1, which gives us this point, U double prime. Alright, now that we got that, all we need to do is connect the points with a line. Bam! There we go. Now we have a half-size quad, which gave us quad double prime. And as usual, if we were to connect all of the corresponding points with each other, they should go through the same line. So let's see what that looks like. So that connects D, D prime, and D double prime, as well as U, U prime, and U double prime as well. And we can do the same thing for Q. So all of these points, corresponding points, lie on the same line with the center of dilation. And it looks, well, with all the colors, it looks really pretty. Find the image of each figure for dilation with the given center and scale factor. Draw and label the image. In this one, they gave us a scale factor with that R stuff, even though we could use just SF, whatever. So the center of dilation is the point C on this one, which is actually just the origin, radicale. And this is a scale factor of 3. So each of the lengths we want to multiply by 3. Thank you. And if we can just do this with the vertices of each shape, or the corners, then we should do them with the corners and then we'll connect them with lines. So for example A, which is 3 away, just straight up from the center of dilation. So to find A prime, we would go 9 away in the same direction, 9. And that point right there is our image point for A. B, however, is at a diagonal length, so it's up 3, to the right 2. So that's 1 full measure away from the center of dilation. So we're going to copy that, and that would give us a scale factor of 2. But we've got to do it one more time to get a scale factor of 3. So this point would be B prime. C is a tricky one because C is 0 away from the center of dilation. So to move it 3 times of that from the center of dilation is just where it is. So C prime is radicale. Next up, we'll just connect the points with lines to create our shape. There we go. Triangle A prime, B prime, C prime. So on 3 radicale, once again, we got a center of dilation at the origin. So we'll identify that, radicale. And now we've got a scale factor of 1/3. So for example, R, which is 3 away, we're going to take 1/3 of that, which is 1 away, and it's just straight up, so this radicale would be R prime. It's kind of the same thing as dividing by 3, if you want. So let's look at S next. S is up 6, and then to the right 3. So we got 1/3 of the 6, which is actually up 2. And then 1/3 of the 3 is to the left 1. So this point radicale is R prime. No, S prime. What the heck?
Wait, we already did S prime.
S prime.
Yeah, I know.
All right, next up is T. T goes down 3, and then to the left 9er. So we'll just do 1/3 of each of those. We'll go down 1, and then to the left 3. Which gives us this point at T prime. So this is good. All we need to do is connect the points. Be careful because in the other class they were kind of connecting it to the origin, which is just the center of dilation. It's not actually a point on the shape. And now we have a shape with half the side lengths, 1/3 of the side lengths of the original. All right, this one has a scale factor of 1/2, but the center of dilation now is not the origin. And they have marked it for you guys, radicale. At 8/6. Yeah, very generous. So this one, since the scale factor is less than 1, it should be a smaller shape. Specifically, half the size in length. So which one should we start with, R, S, or T?
S.
S. All right. S is 2 away straight up from the center of dilation. So we're going to cut that in half straight up. And up 1, that is S prime now. T is 4 away to the right. So we'll do half of that, which is right here, 2 away. And that now is T prime. Then finally we have R, which from the center of dilation is down 4, and then to the left 6. So we'll cut those in half. Halfway 2, halfway is 3, and it would meet right here. And this now would be R prime. Well, this is good. All we got to do now is connect the points on the outside of the shape. R prime, S prime, T prime. That's close. Number 5, we have a scale factor of 2 and a center of dilation at 10.3, which again, and this was extremely generous, they marked it for you right here. So, center of dilation, 10.3 with a scale factor of 2, meaning everything is just double the distance away. So T, for example, which is 2 away, we're going to lengthen that to 4 away from the center of dilation, which gives us this point at T prime. Now we could do S with the sloppage thingy, but we can see that it's straight up from T. Specifically, it's 2 up from T. So now, wherever it is, it's going to be 4 straight up from T. So we're just doubling that length, and this now is S prime. Alright, now if we use the same method for R, R is 4 away from T. So from T prime, R prime should be 8 away from T prime. So 8 away should put us right about right here. And this would be R prime, which doubles the size of that shape. And all we need to do now is connect the points. Now just again wants to show, just to show this, T and R and T prime and R prime are on the same line, but S right here we can see is also on the same line right there. Alright, we'll graph this in a moment. However, it just says with a dilation with the center of dilation at the origin, triangle ABC to triangle A prime, B prime, C prime. If AB is 3 and A prime, B prime is 6, what is the scale factor of the dilation? Well, we can see that 6 after the transformation is 2 times as big as 3. So the scale factor is 2. If B prime, C prime is 8, then what is the length of BC? So BC is the preimage, so it would be half of the 8, which is 4. If AC is 5, what is the length of A prime, C prime? So yeah, we're just going to double that to make it 10. If the sloppage of AB is 0, what is the sloppage of A prime, B prime? Yep, it's got to be the same sloppage. If the slop at A prime, C prime is 4/3, what is the sloppage of AC? Now we could cut those in half, but ultimately after we simplified, it would still give us the same sloppage of 4/3. So if you did put 2 over 1.5, just to show the distances, that's fine. So create a picture of this dilation on the grid below using the information from parts A through E and the additional pieces of information below. Remember that the center of dilation is the origin. The sloppage of CB is undefined, which is good for us to know. And A also is at the origin, which is kind of more important for us to know. All right, let's identify A, which is at the origin. Right here. A. And AB is 3. It told us the sloppage of AB is 0. So if I made it a sloppage of 0, that means it's just a flat, straight line horizontally. But it didn't, yeah, it did say AB is 3, so it's a horizontal line, 3 away from the center, from A rather. There we go. So that point right there is B. Well, on E, it said that the sloppage of AC is 4/3 as well. And also, CB is undefined, which is a straight up and down line, which is one of the bullet points. And, well, AC is 5. Let's see if that helps us. Oh, BC is 4 on part B. So we know that B to C is 4 straight up and down. So that would be where C is. And if we connect A to C, that does give us a sloppage of up 4 to the right 3. So it is also true for E right there. Now the scale factor is 2. So we know that A and A prime are the same point because the center of dilation is at the origin. And AB is 3, so A prime B prime should be 6. So this is where B prime should be. And BC is 4, so B prime C prime should be 8, which gives us this point radicale. And C prime. And then we just connect the points. Now it is possible to have interpreted this differently. So a sloppage of 0 could have given us B prime radicale, or B rather. And then a sloppage undefined with a length of 4 would have given us C radicale. And that still has a sloppage from C to A of 4/3, which just expands that out a little bit too. So there we would have had those other points. A prime is still in the same place, but then we would have had this shape. Something like this. Either way. Determine the length of the radius of this circle whose circumference would be twice as large as the picture above. Circumference is perimeter. So if we scale the perimeter by 2, then we would scale all the lengths by 2, including the radius. So if that's 3 centimeters, then the new length of the radius would be 6 centimeters. This next question is a little tricky though. Determine the length of the radius of a circle whose area would be twice as large as the circle pictured above. So to do that, we need to figure out the area of this circle up in count. And this area is going to be the radius, 3, times the radius, 3, times a pi. And it will be better for us to leave this in terms of pi. So the actual area would be 9 pi centimeters squared for the area. Now this one, B, says that we are taking the area and doubling it. It's twice as large. So the area of this one, down the count, 18 pi centimeters squared. Now this is not the answer for B though, because the question is, what is the length of the radius? Well, the radius in relation to the area is radius times pi. So the pi we're not so worried about. We can tell that the 18 would be the same as the radius squared. So the radius squared equals 18 right now. And to solve these, we'll just square root both sides. And that gives us the radius of the square root of 18 in centimeters. However, we need to simplify the square root of 18. We can simplify these, 9 and 2, 3 and 3. So we got a pair of 3's radicale and a 2. So the square root of 18 is really 3 times 3 times 2. And with this pair of 3's, remember they go on a date or something like that. So they go on one date times the square root of whatever's left of 2. So this is actually 3 times the square root of 2 in centimeters for the radius radicale.